in this equation, we're going to have to use period is equal to 2 times pi times the square root of the mass over the spring constant. We're trying to solve for k. So the first thing we'll do is divide both sides of the equation by 2 pi, which cancels 2 pi. Then we'll square both sides of the equation. And by squaring both sides, it cancels the square root on the right-hand side. Then we're going to do something really strange. We're going to take the inverse of both sides. So on the left side, we're going to flip the equation 2 pi over t squared, and on the right side we will flip that equation to be k over m. It's okay to do that because whatever you do to the left side, as long as you do the same thing to the right side, it's mathematically legitimate. Now we can multiply both sides of the equation times mass, which will cancel mass on the right hand side, leaving us with k equals. And so, shift this around a little bit. So let's plug in. The mass is 0.30 kilograms times 2 pi over the period, which is 0.24 seconds. All of that squared is going to equal the spring constant. And realize that the squared at the top really means you're squaring both the numerator and the denominator. So this should be 2 pi squared and 0.24 squared. And once you solve the equation, you end up with 210 newtons per meter. Number 10, we are trying to determine the frequency that would be heard by a listener if a vehicle were approaching them. So what you have here is a person who's walking on the side of the road, and approaching them is a vehicle that's honking their horn. Okay, but the person is facing this way. So the vehicle, they're hearing the sound from behind them, which means you want to use the equation F LB is equal to the frequency of the source times the velocity divided by velocity minus the velocity of the source. And when we say velocity, this is referring to the speed of air. I'm sorry, the speed of sound in air. And so we have to take our 72.0 kilometers per hour, and that's going to be our velocity of the source. And we're going to convert that to meters per second. 1 kilometer equals 1,000 meters, and 1 hour is equal to 3,600 seconds. This is going to give us a velocity from the source of 20 meters per second. Now we need to determine what is the velocity of sound, and we have to adapt it to the air temperature, which is 25 degrees, so 331.5 plus 0.6 times 25 is going to give us a velocity of 346.5. So now that I have these two taken care of, I can go ahead and plug in and solve my equation. And so the question is still, what frequency will the listener hear if the frequency of the vehicle is 550 hertz times the velocity of sound, 346.5, divided by sound minus the velocity of the source. And so when we solve this, we end up with a frequency of 584 hertz. Number 11, I want you to determine the intensity of the sound. And we're going to use intensity equals power over area. Remember that area is equal to 4 pi r squared. And so we will take intensity equals the power, 50.0 watts, divided by 4 times pi times the radius, which is 2.85 meters. And that's squared. When we solve this, we get 0.49 watts per meters squared. Part B is asking us to determine the relative intensity, which is going to be our decibels. And so we're going to determine relative intensity, which is equal to 10 times the log of the intensity, which we just solved for, 0.49 watts per meter squared, divided by 1 times 10 to the negative 12, which is the threshold of hearing. When we plug this into our calculator, we get 117 decibels. Number 12, we're dealing with an open-ended tube, in which case we're going to use the equation wavelength is equal to 2 times the length plus 0.8 times the diameter. And we're also going to need to use the equation velocity is equal to wavelength times frequency. So first thing I'm going to do is take the temperature, and I'm going to determine the velocity of sound. 331.5 plus 0.6 times 38 gives me a velocity of 354.3 meters per second. So that's my velocity of sound. And so now I'm going to use that with we're trying to determine the frequency. So now I need the wavelength. And so we'll determine wavelength is equal to 2 times the length of the chimney is 5.2 centimeters, which in meters is 0.052 meters, plus 0.8 times the diameter, which is 18 centimeters, or 0.18. So the wavelength, when we type this into our calculator, is 0.392 meters. And so finally, I will take the velocity and the wavelength, and I will plug it into the equation velocity equals wavelength times frequency. To solve for frequency, I will divide both sides by wavelength. This causes wavelength to cancel, leaving me with just frequency. So the frequency equals the velocity, 354.3 meters per second, divided by the wavelength, 0.392 meters. So frequency equals 904 hertz. Number 13, we are dealing with a tube that is closed on one end and open on the other. So this is going to prompt us to use the equation. Wavelength equals 4 times the length plus 0.4 times the diameter. We'll also need the speed equals wavelength times frequency equation. Again, we're trying to solve for frequency. First, I'll go ahead and get the velocity of sound from the temperature. So 331.5 plus 0.6 times 21.5 is going to give us a velocity of 344.4 meters per second. Now I'll determine the wavelength. 4 times, it's 23 centimeters tall, so 0.23 meters, plus 0.4 times the diameter, which is 4 centimeters, so 0.04 meters. When I solve this, I get a wavelength of 0.984 meters. And now I can use my velocity and my wavelength to solve velocity equals wavelength times frequency. Again, divide both sides by wavelength, cancel the wavelengths, and this leaves me with the frequency equals the velocity divided by the wavelength, and that's going to equal 350 hertz. Number 14, we're going to use velocity equals wavelength times frequency. However, this is not the speed of sound. It's the speed of light, which they give to me, and that's the speed I'm going to use right here as my velocity. So 3 0.00 times 10 to the 8 meters per second is equal to, we want to know what is the wavelength, but they give me the frequency, which is 9.00 times 10 to the 9 hertz. Frequency and this symbol right here are identical. So I'm going to divide both sides by 9.00 times 10 to the 9 hertz, which cancels it on the right. And so wavelength will equal 0.03 meters. Number 15, this is our last one. We are still going to use the speed equals wavelength times frequency. And what they're asking us is, what is the possible range of wavelengths for these instruments? And we do have the speed of air in this case, and we have two different frequencies, so we're going to have two different answers. First, I'm going to rearrange the equation to solve for wavelength. Divide both sides by frequency, cancels out frequency on the right. So wavelength equals velocity divided by frequency. So the first one is going to be the wavelength equals 340 meters per second over 196 hertz, which is going to be equal to 1.73 meters. And the second one is going to be 340 meters per second divided by 2637 hertz, which is equal to 0.129 meters. So this is my range of wavelengths and that range of frequencies.